Hello, this is going to be a live recording. Sorry, I just need a bit of peppiness. It's actually been recorded in the 2 o'clock Tuesday lecture because there is no recording. I do not know what the quality is going to be like because normally I record in the middle of the night. So let's hope. So today we're doing sequence series and power series, an introduction. If you've had problems downloading the actual slides, you just need to retry when you download and it should come up. Okay. Now, this particular lecture is actually 2 weeks of lectures collapsed. It's not going to be an issue next year because we'll be starting in prep week, the lectures program, because it's usually a 12-week program. So bear with me. Okay. The reason for sequence series, right. So in this lecture, we begin to look at the topics of sequences and series. We're going to extend this to consider particular kinds of series of functions called power series, okay, which are used to solve more difficult differential equations and also replace transcendental functions in certain cases. What we're talking about in this case is trigonometric, exponential, logarithmic, and hyperbolic functions. The thing about power series is you must consider the radius of convergence, but we're only going to be touching on this in this lecture because we don't have as much time. I will tell you what I believe is important for this semester, okay? This semester being spring 2017. You realise I have no idea whether there's going to be interference because I'm wearing a microphone and I normally don't wear a mic, okay? Right. What do we know about geometric series and sequences? This here is an example, and you probably remember geometric sequences from high school. Okay, so here we have, as an example, a geometric sequence. This is term 1, term 2, term 3, term 4. And since it's a geometric sequence, the common ratio is going to be term 2, or I should put n plus 1 over an. So 20 over 10, which is actually 40 over 20, which is 80 over 40, or 2. So our position and our term, we have position 1, 2, 3, 4, and n. So our term was 10, 20, 30, 40. This here is 2 to the power of 0 times by 10. That is 2 to the power of 1 times by 10, which is 2 to the power of, what have I done wrong?
40, 80.
Yeah, 40, 80. See, this is now recorded forever. Well, at least until I delete it. Okay. So, we have 2 to the 2. Oh, you know what's really good? Now I've got you guys here so I can ask you a question and then that is recorded here. So 40, 80. And lastly, 2 to the 3 times 10 to the 10. So our term, or an, is a1 r to the n minus 1. So we have an here is equal to 10 times by 2 to the n minus 1. So this is actually for n is equal to, well, 1, 2, 3, etc. Now, this is a geometric sequence. A geometric series, on the other hand, is adding. Bless you. We're going to add it up. So you can actually have the terms of the geometric series as 10, then 10 plus 20, so it's 30, then 10 plus 20 plus 40, so it's 70, etc. Okay? Okay, I'll give you guys some time to write that down. Okay, so, can I turn the page? Yeah. Have now some other examples which are geometric. If they're geometric, identify the common ratio. So if we're looking at this sequence, is this a geometric sequence? I mean, the easiest way to find out is just look at the common ratio. So, common ratio, A2 over A1. Well, that's going to be 101. A3 over A2 is 1001 over 101. Is this 101? No. So that does not equal 101. So it's not geometric. Okay. Then we got 1, 4, 9, 16, 25. This here, okay, can be written as curly brackets n squared, because it is 1 squared plus 2, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Okay, this notation refers to the whole sequence. It refers to the whole sequence. Okay. Now, for this sequence, the series will actually be 1 plus 101, bless you. That is now part of the recording, which is not necessarily a bad thing. We could actually do the statistics of how many sneezes we have in a lecture, whether it's affected by what room you're in, etc. Just saying. These poor people who are going to be listening at home. They're really bad jokes. Okay. So we've got 1 plus 4 plus... I apologise to you people at home for the poor jokes which you've been missing in all previous recordings. 1 plus 4 plus 9 plus 16, etc. is the series for this one. Then we have here. Now, is this a geometric sequence? If we take term 2 divided by term 1, that gives us minus 0.1. And if we take term 3 divided by term 2, guess what? Therefore, this one is in fact geometric. Okay. Now, this one here, we also have the sum. So our geometric series can be represented as 1 plus 4 plus 9 plus 16, etc. This is this Greek, this here is the Greek symbol, capital sigma, okay? So we could have also had, say, another example of minus 1 to the power of n. This is actually minus 1 to the power of 1 plus minus 1 to the power of 2 plus minus 1 to the power of 3. So we've actually got minus 1 plus 1 minus 1, which is equal to minus 1. And of course, if you take n to the 4, it'll actually be 0. Okay. So we have one more here. This one will have a sequence. Now, when n equals to 1, we've got minus 1 to the power of 1, 1/3 to the power of 1. Then we have minus 1 to the power of 2, 1/3 to the power of 2. Then we got minus 1 to the power of 3. And yes, you can have minuses in a sequence, etc. So this, if we work it out, minus 3, that one goes to a positive, so 1/9, negative 1/27. Now if I divide this by this, So 1/9 divided by 1/3. We'll have, no, that's negative there. That will be, what? Minus 1/3. Then we'll do A3 divided by A2. 27 divided by 1/9. So that's 9/27 negative. Is this geometric?
Are we not going to flip over the minus 1/3 or 1/9? So it's 3/9, which is minus 3.
Minus 1/3? If I flip this,
yeah.
So 1/9 times by 3/1 is 3/9, which is minus 1/3. Okay? So this one here. So do you guys want a bit of a lesson in multiplying fractions? Oh yes, come on. Let me do this for you. It's so good having an audience. Do you have any idea what it's like recording in the middle of the night? So, when we have 1/a divided by 1/b, this is the same as 1/a times by the inverse of b/1, so we end up having b/a.
Thank you.
Okay? So, this will actually give you minus 1/3. Is this a geometric sequence? Yeah. Okay. Now, this one here is simply saying 1 squared, so this is actually the Greek capital for pi, and it's used for a continued product. What this basically means is 1 squared times by 2 squared times by 3 squared. So in this page we're really learning some symbols as well. Okay? So let's move on. So we have page sequences and their definitions. A sequence of real numbers is a function whose domain is the set of positive integers. The values taken by the function are called the terms of the sequence. Terms of the sequence may be defined in various ways, including explicitly. Example, fn is equal to minus 1 to the power of n cubed, okay? Or even iteratively, where we've got x1 is equal to 10, xn plus 1 is equal to 5x to the xn. So if we look at this, what this is x1 is equal to 10, so x2 is 5 times by x1, which is 5 times by 10, so it's going to be 50. x3 is 5 times by x2, because x3 is equal to 5 times by x2. So it's 5 times by 50, so it's 250, etc. So this is actually discrete mass. I've got that as a note in my set here. Okay. Now, there is also limits of sequences. A sequence, an, is said to be convergent if the limit of n goes to infinity of an exists. Otherwise, the sequence is said to be divergent. To establish convergence of sequences, some examples and theorems are needed, and that's what we're going to do now. So did I go too fast? Has everyone finished writing? Yeah? Oh, good. Okay, so consider this sequence. 1/n, which is equal to 1, half, 1/3, and 1/4. What happens to the numbers as n increases? So let's just pick a large number, say 1,000, or even 1,000,000. So what's actually happening as n goes to infinity? It goes to 0. So as n goes to infinity, the terms go to 0. What we write, limit of n goes to infinity of 1 over n is equal to 0. Okay, so it tends towards 0. What about 7 over n? If we put in a large number, say 1,000, we have 7 over 1,000, 7 over 1,000,000, keeps going. So the limit as n goes to infinity of 7 over n is equal to 0. It's quite obvious, but nonetheless, one sometimes has to think about it. So basically, the limit of n goes to infinity of k over n is equal to 0 if k is a constant. Okay? What about this one here? We have 1 over n squared is equal to 1, 1/4, 1/9, 1/16, and of course, the limit as n goes to infinity of 1 over n squared is equal to 0. Okay? There is something in mathematics we do not write. That's what we don't do in maths. Surprisingly, we do it quite often in physics. Yeah. So, because we just say in physics, it's just gone really small. It's always 0. Yep. We shouldn't do it, but we do. Okay. Anyway, we can generalize. If p is an integer greater than or equal to 1, and k is constant, then, so p is greater than or equal to 1, the limit of n goes to infinity of k over n to the power of p is equal to 0. So we're just generalizing there. Say that again? Okay. Sorry, you guys missed the joke at home. All right. So we're ready to turn the page. Okay, there's some useful results. Let xn be a sequence converging to x naught, and let yn be a sequence of converging to y naught. Then, these are just useful results that you might want to use later. We have the sequence of xn plus minus yn will go to x naught plus minus y naught. Okay, the sequence of k times by xn will go to k times by x naught. The sequence of xn times by yn will go to x naught times by y naught. Okay, and we also have the sequence of xn over yn goes to x naught over y naught, provided that y naught does not equal to 0, okay? And that yn is never 0 for any n, okay? These are just 4 results that are useful.